Welcome to our presentation on vector autoregression, or VAR, models. This is a fundamental tool in advanced time series analysis. We will cover the theory behind these models and demonstrate their practical application using the Eviews software. The core idea, inspired by the general equilibrium principle, is that in many economic systems, everything depends on everything else. VAR models provide a framework to capture these complex interdependencies. Imagine trying to understand the relationship between inflation, unemployment, and interest rates. A VAR model allows us to see how a change in one variable, like an interest rate hike, dynamically affects the others over time. So why do we need a special model like VAR? Let's start by looking at a common problem in econometrics that VAR models are designed to solve: endogeneity. In traditional single equation models, like OLS, Model A, we assume a one-way causal street, where an exogenous variable x affects an endogenous variable y. However, in macroeconomics, the reality is far more complex. Variables like GDP, interest rates, and money supply aren't purely exogenous. They evolve together, influencing each other simultaneously in intricate feedback loops, as depicted in Model B. VAR. The flaw in single equation models is that they bias results by ignoring these crucial feedback loops and fail to capture the complete system dynamics. The VAR model provides a robust solution by treating all variables in the system as endogenous from the outset, allowing us to directly model their mutual interdependence. For instance, higher GDP might lead the central bank to raise interest rates, but higher interest rates can, in turn, slow down GDP growth. A single equation model can't capture this two-way relationship, but a VAR model can. This slide presents a roadmap for system estimation, starting with a crucial first step: checking data stationarity. If your data is non-stationary, specifically I1 and co-integrated, the appropriate model is a VECM, or Vector Error Correction model. However, if your data is stationary, denoted as I0, you should proceed with a standard VAR model. Once you're on the path to a standard VAR, your objective determines the next step. If your primary goal is forecasting, you'll use an unrestricted, or reduced form, VAR. But if your aim is policy analysis or testing economic theory, a structural VAR, or SVAR, is the correct choice. As highlighted in the stationarity first note on the right, VARs fundamentally require stable data, meaning all roots must lie inside the unit circle to ensure valid results. Then, the theory second principle guides your choice between an unrestricted VAR, which lets the data speak freely for forecasting, and an SVAR, which allows you to impose economic theory to gain deeper insights into policy effects. This slide presents the mathematical framework for an unrestricted vector autoregression, or VAR, model of order P. The core equation, yt equals c plus a1 yt minus 1 plus plus ap yt minus p plus et, is what we use to model the dynamic relationships between multiple time series variables. Let's break down its components. Yt represents a vector of endogenous variables at time t. For example, this could include macroeconomic indicators like GDP, M1 money supply, or the consumer price index. The terms A1 through AP are matrices of lag coefficients. These matrices are crucial as they capture the dynamic interactions between all variables in the system across P different lags. Finally, ET is a vector of white noise error terms, often referred to as innovations or shocks, representing the unpredictable component of the model. A key insight of the unrestricted VAR model is that every variable in the system is regressed on its own past values and the past values of every other variable in the system. This comprehensive approach is how the model captures the rich interdependencies. Regarding its structure, the unrestricted VAR is in a reduced form, meaning there are no simultaneous variables on the right-hand side of the equations. This simplifies estimation. The estimation method for this model is typically equation by equation ordinary least squares, or OLS. This method is consistent and efficient for estimating unrestricted VAR models. However, it's important to note the parameters. The number of coefficients in a VAR model can proliferate very quickly, specifically n-squared coefficients per lag, where n is the number of variables. This can quickly lead to an overparameterized model if not managed carefully. This slide outlines the critical assumptions and stability conditions for our VAR models. First, we have stationarity. All variables must be integrated of order 0, or I0. If they're not, you need to either difference the data or use a vector error correction model, a VECM. Second is lag selection, where we face a trade-off between bias and efficiency. We use information criteria like a CACE or AIC and Schwartz or SC to choose the optimal number of lags. When making this choice, especially with small samples, it's generally better to favor the Schwartz criterion to ensure parsimony and avoid overparametrization. Third, and crucial, is the stability condition. The model must be stable, meaning all inverse AR roots must lie inside the unit circle. This is a vital stability check, because if any roots are greater than 1, the model will explode, and its impulse responses, or IRFs, will not decay, rendering the model invalid. To begin in Eviews, you navigate to Quick, then Estimate VAR. This opens the main specification window. In the Endogenous Variables box, you list all the variables in your system, separated by spaces. The order you list them in can matter, especially for structural analysis later on. Next, you specify the lag interval. For example, 1, 2 tells Eviews to include the first and second lags of all variables in each equation. Finally, you can include deterministic variables like a constant or a trend in the Exogenous Variables box. For a standard VAR, the Standard VAR radio button is selected by default. A critical warning. Do not try to interpret individual VAR coefficients directly. They often oscillate in sign and magnitude, making intuitive interpretation nearly impossible. Instead, we focus on the system's overall dynamics visualized through graphs. To answer, how does a shock in one variable affect another over time, we use the impulse response function, or IRF. It traces the dynamic impact of a shock. To understand what proportion of a variable's future movement is due to shocks from other variables, we use variance decomposition. And to check the fundamental assumption of is the model stable, we examine the AR roots table or graph, as we discussed earlier. This slide presents a case study on selecting the optimal lag length for a 3-variable system involving GDP, M1, and interest rate. The table displays Eviews output for various lag length criteria across different lags, from 0 to 4. To obtain this table in Eviews, you would select View, then Lag Structure, followed by Lag Length criteria. You'll notice that for lag 2, both the AIC and SC criteria are marked with an asterisk, indicating they suggest an optimal lag length of 2. A crucial heuristic to remember is that if the AIC and SC criteria differ, the Schwartz criterion, or SC, is generally considered safer for smaller samples because it is more parsimonious, meaning it favors simpler models. The next step, once an optimal lag is identified, is to input the suggested lag, in this case 2, back into the VAR estimate dialog to refine your model specification. This slide illustrates the crucial AR root stability test, which examines the inverse roots of the AR characteristic polynomial. The graph shows a unit circle on a complex plane, with blue dots representing the inverse roots. The model passes the stability test if all these dots lie strictly inside the unit circle, indicating that the VAR model is stationary and stable. If even one dot is on or outside the unit circle, the model fails this test, signifying that it is non-stationary or unstable. The fix for a failed stability test typically involves re-evaluating the stationarity of your variables, potentially by first differencing them, as in dGDP, or by checking for co-integration and then using a vector error correction model, or VECM, instead of a standard VAR. This slide visually explains impulse response functions, or IRF. An IRF traces the effect of a 1 standard deviation shock to one of the innovations on the current and future values of other variables in the system. The solid blue line shows the estimated response path of a variable, while the dotted red lines represent the confidence intervals, typically at plus or minus 2 standard errors. The effect of the shock is considered statistically significant if the confidence interval does not include the horizontal zero line. If it crosses or includes zero, the effect is statistically insignificant. In the example shown, a positive shock to interest rates, labeled shock 3, causes a statistically significant decline in GDP, or gap, over several periods. The main purpose of a structural VAR, or SVAR, is to move from purely statistical shocks to economically meaningful ones. We want to isolate specific economic shocks, such as a monetary policy shock, from general noise present in the data. The core of this is understanding the equation A times E subscript t equals B times U subscript t. Here, E subscript t represents the reduced form residuals, which are typically correlated and lack direct economic meaning. Our goal is to transform these into U subscript t, which are the structural shocks that are uncorrelated and economically interpretable, like a supply shock. This transformation is achieved through the structural matrices A and B. The key challenge here is the identification problem. How do we impose enough restrictions on A and B to uniquely determine these structural shocks? One common approach is Cholesky identification, which imposes a recursive ordering. This method dictates that the A matrix is lower triangular, meaning that shocks propagate sequentially through the system. This implies that variables appearing earlier in the specified ordering can affect variables later in the ordering contemporaneously, but not vice versa. This concept, ordering matters, is critical. Variables at the top of the ordering affect others instantly, while variables at the bottom respond with a lag. Choosing the correct ordering is crucial and should be based on economic theory. To specify an SVAR in Eviews, you first estimate a standard VAR, then go to proc-estimate structural factorization. Eviews provides a flexible text-based system for entering restrictions on the A and B matrices. The code view shows examples like at A12 equals 0 and at A13 equals 0, along with at diag B. This syntax forces contemporaneous interactions to 0, meaning, for instance, that variable 2 cannot instantly affect variable 1 when at A12 equals 0 is imposed. This text-based flexibility makes it easier to replicate complex identification schemes from academic papers, such as those by Pearsman, 2005. For more advanced analyses, you can impose restrictions on specific lags of variables directly within the VAR estimation dialog using the VAR Restrictions tab. This feature is particularly useful for testing hypotheses like Granger causality or exogeneity within the system. By setting the coefficients of all lags of a variable to 0 in a specific equation, you are essentially testing if that variable can be excluded. For example, setting L1, 2, 4 equals 0, as shown in the image, excludes the first lag of the fourth variable from the second equation of the VAR system. If these restrictions are theoretically valid and supported by the data, this creates a more efficient subset VAR model by reducing the number of parameters that need to be estimated. Eviews allows for efficient automation and custom reporting by using data members, which are accessed with a dot syntax. The general syntax is object_name.attribute_member_name. This enables you to programmatically pull results like coefficient matrices or structural matrices directly from your estimated VAR object. For example, myvar.svar matrix retrieves the estimated structural matrix A, myvar.svarb matrix retrieves structural matrix B, and myvar.coef matrix retrieves all coefficients. You can also use commands like freeze_mygraph, myvar.impulse, to save an impulse response function graph as a separate, permanent graph object in your work file for later use in reports. Here are some references and further reading materials for those who want to delve deeper into VAR models. First, consult Eviews User Guide 2, specifically chapters 33 and 34, for detailed Eviews-specific guidance. For a strong theoretical foundation in econometrics, I recommend Gujarati, D.N.'s Basic Econometrics. And for practical Eviews applications, see Oliari's, S. et al.'s Eviews Illustrated. As a final thought, remember that while VAR models are excellent for letting the data reveal its own story, structural VARs are crucial when an economist needs to inject theoretical meaning